So let's take a look at that. Now, there will be a time limit on the quiz tomorrow. I'm going to stop you about 20 minutes short, probably, of the class being over, and we're going to talk about some of. There's going to be a small assignment today based on the new thing that we talked about here at the end of the period, just a few problems. Mostly your homework is to get ready for the quiz and review and go over stuff like that. But let's just take a look here. On the board, I've got, I guess, are we missing anything? All right, so on the board here, I've got kind of the main ideas that are going to be talked about on the quiz. All right, so you look at, we're talking about sections 1, 2, and 3 in chapter 5. So if you remember where we started, chapter 1 was about geometry areas, mostly. I mean, that's a big part of what section 5.1 was, just an introduction into, so this part right here, this 5.1, was this geometry area kind of thing. Now, if you remember in the book, now this is actually a picture from 5.2, but this would have been the kind of stuff that we ask in section 5.1, where we would just look at a picture like this, and we would say, okay, this is the little f graph right here, this is little f. So we would say, what's the area from, say, 1 to 5 under little f? And well, it's just this area. So you could just do a triangle for me, find that area. Or maybe we were going to do this area here, and that would be a circle for me. Okay? Now, I was talking with some people before school. Don't worry too much about the circle formula. I mean, this is the formula of a circle. So if you're given this integral, everything else we did was lines, triangles, trapezoids, that kind of stuff. This is a circle. It doesn't ever look any different than this. This is the radius squared right here. So this would just be a circle at the origin, -3 to 3, right? And then it would just be a half circle, pi r squared divided by 2. Okay? So it always looks like that with a square root, x squared, that's always minus. I mean, but I don't see that being a big thing. I'll probably just give you a picture like this and ask you to vary. Okay? Now, another thing we did talk about in that section was absolute value. What if I asked you for the absolute value of f? And that came up on your homework here a little bit. What if I asked you about the area from -5 to 1 of the absolute value of f? What would you do? Just flip the circle up. I mean, that's what absolute value does. Absolute value just takes anything that's negative, any outputs that are negative, and makes them positive. So all you would do is just flip the circle up. And then all this area plus this area would be positive. So you just do that. Okay, now, on your homework, there were some absolute value ones we can talk about that kind of thing here as well. But it just makes that area positive. Oh, one other formula we have that I should mention was the average value. There weren't a lot of problems about that, but that was on there. And let me see, I think I've got that here somewhere. Right there. The average value of a function f, you need to know that formula, okay? And then that would fit in, it's just the integral from a to b, so the area, the definite integral, so the area from a to b, and divided by b minus a. Now, I could ask an average value question in any kind of question where I would ask you a regular definite integral question. Now, in section 1, that was when we were doing areas, like geometry. So any question where I was going to do this here, where I was going to do an integral from a to b, we can do an average value question, because that just says do the integral from a to b and then divide by b minus a. So if we were doing a geometry one, like we were just looking at, I could ask you the average value of this function from -5 to 5. Well, you would do the area from -5 to 5, and you divide by 10. Right? B minus a, 5 minus -5 is 10. So you do the area divided by 10. So that could be an average value. Now, later on then, like the homework you had today, was a bunch of definite integrals, except you were doing the fundamental theorem part 2. You were doing f of b minus f of a. Well, you could do an average value problem where you do that, f of b minus f of a, come up with that answer, and divide by b minus f. That's an average value. Yeah. Just another way to do it. Okay. So, yeah, so when we list these things here, they're just different ways to solve. Matter of fact, that would be a good one. That would be a good review problem to just do real quick here. Let's do this integral right here. Let's do, well, let's do number, we were just talking about it at lunch today. It was an absolute value, so that would encompass it on the absolute value and everything. So let's say I gave you this right here. Let's say I gave you this function, the old b here, right? And I said I want you to do this integral from -1 to 1. Wasn't that number 21? I think that was number 21 in the pack. Okay. Now, because like Sydney was just saying, we've done these a variety of different ways. As we've moved through chapter 5, we've learned additional things, and so we have multiple ways of doing these problems. So the first way we learned how to do a definite integral is straight geometry. So if you look at this problem, you graph it, -1 to 1, you're just talking about the area of these two triangles, right? Well, what's the area of this triangle on the left? 1 times 1 is 1, half of that is a half. So that'd be a half. What's this area? Also a half. Half plus a half, 1. Area is 1. So that's one way to do it. So if that problem was on the quiz, that's fine. Do it that way. Now, I think I probably will have some on there that say use the fundamental theorem. Now, to be honest, those are going to be ones where that's the only way to do it, so you don't have to make that decision. Okay? So the answer is 1. Now, we then went through section 5.2 and all this stuff, antiderivative chart stuff, and then we said, hey, antiderivative, yeah, we can use that to find area. That's where this fundamental theorem part 2 came from. We can do big F of B minus big F of A. Now, the problem is, how do you do an antiderivative of an absolute value? Well, you don't. What you do is you break it into its two parts. So what you do, if you're going to do an absolute value problem, as an antiderivative, you have to do, well, what's the equation of this piece? That's y equals x. What's the equation of this piece? Y equals -x. So what you would do with this is you would say, okay, let's do the integral from -1 to 0 of -x dx. And then we would do the integral from 0 to 1 of x dx. Right? Now, in this one, you would say, well, this is not harder than triangle. This triangle would have been way to go. This is stupid. Right? Yeah, probably right. Okay? But what the heck? I think it's fun. So, let's do our antiderivative. So, what's the antiderivative of -x? Raise it up to a 2, divide by 2, right? That's how we do antiderivative. Raise it up 1, divide by the new power. So it would be -1/2 x squared from -1 to 0. And this one would be what, antiderivative? 1/2 x squared from 0 to 1. Let's do it. So on this f of b minus f of a, so we plug in a 0. 0 times 0 is 0. Minus, what happens if you put a -1 in? -1 squared is 1 times -1/2. You get 0 minus -1/2, which is half. Oh yeah, that's what we said. Okay, plus, on this one, f of b minus f of a, plug in a 1, we get 1/2 times 1 is a half, minus, put in 0. Oh, you get 1/2. What did you get? 1/2 plus 1/2? You 1, right? You get the same answer. So back to your question, you get the same answer? Yeah, just a different way of doing it. Okay, we have an option here. In that problem, we could do geometry, or we could do this. Okay, well, let's go to number 24. I told you guys I wasn't going to do number 24, but here we go. Okay, on 24, it says -1 to 1 of x cubed dx. How do you graph x cubed dx? Well, the same way you graph any absolute value. You graph it like normal, and do what? Flip it. The part that's negative would flip up to here. So -1 to 1 would be those two areas added together. Now, how are you going to do that? Did that make triangles? You can't do geometry, see? You can't do geometry. You've got no choice but to do fundamental theorem part 2 with antiderivative. Now, how do we do it? Well, what are the two pieces? What's this piece? No, that's cubed. And what's this one? Negative x cubed. Because we just made it opposite, because we flipped it. Now, there's a lot of ways you could think about this one, to be honest with you. Because there's symmetry, don't we know these two areas are the same? So couldn't I just do the piece that's the normal x cubed from 0 to 1? I could just do that one and then double it when I'm done. Right? I could just do the area from 0 to 1 and then double it when I'm done. So I'd have 1/4 x to the 4th, my antiderivative, 0 to 1. Right? Plug in a 1, I get 1/4. Plug in a 0, I get 0. And there it is, 1/4. Now I double that, so my answer would be 1/2. Right? Double. Or somebody else actually suggested this, which I thought was a good idea. Instead of even flipping that up, just picture in your head that it's going to be flipped up. And let me do this in red. And what they were saying is just find this area, which would be 0 to 1, and find this area, which would be your normal x cubed from -1 to 0. Just do that. Now that's going to come out what? That's going to come out negative, but what do? Make it positive. Make it positive, because you know that absolute value flips it up here. It makes the negative area positive. So don't even worry about flipping the graph up. Just do it, and then count all the negative areas positive area. But you do have to split it. You can't do it all the way from -1 to 1, because you get 0, because the positive and negative will cancel out. So kind of back to this problem. What if I had you do the absolute value of this? We said flip this up. Well, you could flip it up, or you could just do the area, just do this area, call it positive. Do this area, which is negative, but call it positive, because you know it would be flipped up. You see what I mean? You don't have to literally flip it up. You can just do that area that's below, and then just call it positive. And that's what you do with absolute value. Okay, and now where did I start doing this? I was talking about average value. Right? So if I ask for the average value of this function from -1 to 1, we would just do this integral from -1 to 1. If I wanted the average value of absolute value, that's cubed, right? So the average value formula is just one you got to make sure you memorize. It's just the integral divided by the b minus a. So any problem where we can do an area, an integral, in any one of these different ways, we can do an average value just by dividing by b minus a. Okay. So let's back up here a little bit and talk about this in order. So in 5.1, we just learned those basic areas with geometry. All right. Then we went into the 5.2 stuff and did all that. I'll talk about that in a minute. And then we learned this antiderivative thing was kind of important. We got into f of b minus f of a. We just did a few examples, kind of a tough one with after that. But we'll get back to doing some of those here in a minute with 5.3. And we learned fundamental theorem part 2. So that's how we do these definite intervals. And then we had this whole thing with area function. That was the real big part of it. So when we look at the quiz, if I had to roughly say what the quiz is about, this is kind of a small part, maybe a quarter, maybe a fourth, I don't know, I don't know exactly. But this is a small part, few of these, but we're going to be doing a lot more of this antiderivative stuff in the next week. So maybe a quarter here, less than that probably. And then a half or more, a little more than a half would be on this area function, antiderivative, the chart stuff, all of that will be moved. Okay. Hopefully you think that stuff's pretty easy. Now, there'll be certain aspects of this with notation that's kind of tricky that you can't really study for, other than we'll do some examples here and just go back over the homework and just, there's going to be some questions I'm going to ask you that get at, do you understand what's going on? Do you understand the notation and what it means and that kind of stuff? Okay. So, there's going to be some of that. All right, so that's kind of what I have for the quiz. Let's do this real quick, because this leads into something I want to do homework-wise. Well, I tell you what. Before we do that, let's actually talk about this f of b minus f of a, the stuff that was your homework today. Let's do that, because that fits in with this definite integral. Then we'll get into this stuff here. So anything in the packet, those problems that you want to look at. I haven't thought about 15. Okay. What was 18? Yes. 18 and 15 are very similar. 18 says the integral from 0 to 2 of 2 minus t times the square root of t, which I'm going to write t to the 1/2. Okay. ID. Distribute. I will not give you one on the test tomorrow like this. Okay? But, let's distribute this. So what do I get? 2t to the 1/2 minus t to the 3/2. I will give you one tomorrow like that. Okay? Now, one of the things that we'll talk a lot about in the next week as we get ready for the gateway test is, hey, when you see one like this, before you can do the antiderivative, you have to do some algebra to it. You have to do some work to it. That was true in derivatives. Sometimes it was easier to simplify it first before you did the derivative rule. Well, the same thing is true, probably more true in antiderivatives. It's almost always, there's many times something you can do to make it simpler, put it in a form to make the antiderivative easier. I think I've told you guys this, but there are some functions that don't have an antiderivative. You just cannot do the antiderivative. It doesn't exist. I'm not going to ask you to those on gateway test. All the ones I give you on gateway test have an antiderivative. Okay. All right, so I might ask you one like this on the gateway or on the quiz tomorrow. So what do? Raise that up to 3/2, divide by 3/2. Dividing by 3/2 means times by 2/3. What's 2/3 times 2? 4/3. So this would be 4/3 t to the 3/2. Minus, raise that up one, that'd be 5/2. Divide by 5/2 would be 2/5 t to the 5/2. Square bracket, or right bracket, 0 to 2. Now, I didn't do a right bracket on this one because I kept the integral symbol because I hadn't done the antiderivative. All I did was some algebra. After you do the antiderivative, you do this. And notice the dt is not there anymore either. Right? dt goes away because that just meant with respect to t, and that's all. Okay, so now we put a 2 in here. Now, here's something else I won't do to you anymore. I won't give you weird square root stuff. It's no calculator, the whole thing. But if you put a 2 in here, you always want to look at this bottom number, and you do the square root of 2, you can't do it. I mean, right? I mean, you call it square root of 2 cubed. I mean, this would be square root of 8, and, you know, there'd be all kinds of messy stuff. So on this one, go to your calculator, get a decimal. I don't know, the back of the book doesn't even give it as a decimal, or my answer book doesn't even give it as a decimal, so I don't even know what it comes out to be. 16 radical 2 over 15 is what they've got. Yeah, whatever that is a decimal. 16 radical 2 over 15. Now, I might give you one like number 15. That is, except with, because that one comes out a little nicer. So let's talk about number 15, just quickly. Number 15, there's no quotient rule for antiderivatives, okay? So on 15, what you do is you write this as u to the 1/2, and then you split it apart. Split it apart into two separate things. Then you subtract your powers and do that. Now, I won't give you one like that on the quiz, but I might give you one like this. Right? I might give you that thing in the red like that. Okay? So what? You raise that up to what? 3/2? Divide by 3/2, which would be 2/3. Raise this up one would be 1/2. Divide by 1/2 is like times it by 2, so that'd make that 4. So you'd end up with this. Right? You'd end up with this right here. Now, this one works pretty nice. When you put a 4 in here, now think about this. 4 to the 3/2, you do the 2 first. That'd be the square root of 4, which is 2. 2 cubed is 8. 8 times 2/3 is 16/3. Okay? So that, to me, is doable without a calculator. Put in a 1. Oh, excuse me, I got to put a 4 into here. Put a 4 here, and the 1/2 square root of 4 is 2. 2 times 4 is 8. So 16/3 minus 8. Then you put a 1 in. So this is f of b minus f of a. Now you put a 1 in here. 1 to anything is 1, so that'd be 2/3. 1 to 1/2 times 4, that'd be 4. Then you get a common denominator. 8 is 24 thirds, so 16 thirds minus 24 thirds would be negative 8 thirds. 2 thirds minus 12 thirds. 4 would be 12 thirds, so 2 thirds minus 12 thirds would be negative 10 thirds. Add the opposite. 2 thirds. So that one, definitely, you could have something like that. Now, again, I said that's only less than a quarter of the quiz, maybe less. You know, this F would be minus 7. But a couple of them, maybe, a couple of problems. But certainly might get one that's a problem. All right, if you've got any more questions on this, on the homework, the fundamental theorem stuff in the packet, we can. You can look at the answer book and maybe talk about that at the end of the lesson. All right, here's what I'd like you to do next. I'd like you to work this problem right here. Okay? Because there's a couple problems in the book that were on your homework that I want to talk about. So this problem gets to the area function stuff. And this is a big part of the quiz. Understanding this whole area function from a to x, it means antiderivative of f, it's chart stuff. All of those kind of questions. Now, we had talked about when you do a chart problem, where's it increasing, where's the inflection points, where's it concave up, that you could give reasons that were area reasons or you could give slope reasons, because they both work. I'm not going to ask you for one or the other. You give whatever reason you want. You want to give both reasons, that's fine. Okay, but I won't ask you specific. All right, here's what I want you to do real quick. You can visit with each other a little bit. Find the equation for this big F right here. Find the equation for that business, because that could be something that I asked you. All right, is that fine? Will more time help? When I say it's enough time, and you say no, would an hour be enough? 2 hours? You know, 2 hours. One of those things where I don't care how much time you give me, I ain't getting it. I guess that was my rest of the calendar. Now I see where it goes. No, I guess I was making the assumption you actually wanted it. All right. So what are we doing? We want antiderivative, right? That's what that means. And this negative 1 is going to play a key role, because if we know the A, if we know what negative 1 is, it means we know what? We can find the C. Antiderivative is always going to have a plus C on it. Okay, so what's your antiderivative here? Careful.
X squared minus 7x.
Right? Your antiderivative has an X in it. It's got to be an X, not a T. This is the variable right here. This is just a placeholder. Now we'll talk. Now I actually want to show you a different way to do this. Now that we've learned the fundamental theorem part 2, and I don't know if anybody thought of doing that, but when we first did these problems, we had learned fundamental theorem part 2, which actually can work on these, which I'll show you here in a second. So your antiderivative was x squared minus 7x plus c. Now, did everybody remember this part? Right here? Big F of -1, if you put a -1 right there for x, is like putting a -1 right there. The area from -1 to -1 is 0. So this is like giving you an initial condition. So we plug that -1 in. We get 1 plus 7 plus c, which is 8. Subtract 8 from both sides. We get c equals -8. So it would end up being this. X squared minus 7x minus 8. Okay? All right. So that could be a legitimate question on the quiz. Now, oh wait. Okay. Now, watch this. Fundamental theorem part 2 actually worked. Did anybody try this? Accidentally? So you just thought of that? Well, yeah, well that's good. Some people in the other class did that too. Now that we've learned that, I can see where that would come to mind. Now listen carefully to this. Because the notation, here's where notation can get you in trouble. We just got done saying, Sam, that big F of -1 is 0. Big F of -1 is 0. We just got done saying that. That is a true statement. There's nothing that would change that in this problem. Okay? But here's where we get in a little bit of trouble. If you do this thing called the fundamental theorem part 2, which says take the antiderivative and put in b, put in a, and subtract them. That's fundamental theorem part 2. The part we don't usually mention here is what antiderivative are we talking about? Because remember, does the c matter in the fundamental theorem part 2? Because when you subtract them, the c would disappear. So here's what I guess I'm cautioning you about. So what most people do when they think of fundamental theorem part 2 is they think of using big F. So people would think of this and say, well, this would be big F of x minus big F of -1. Does everybody see where I got that? Just looking at this as an integral, say, oh yeah, just big F of b minus big F of a. Now the problem is you'd look at this big F of -1, or a potential problem would be you'd look at big F of -1 and think that's supposed to be 0. It's not. Well, big F of -1 is 0. The problem is we shouldn't use big F here. When we say fundamental theorem part 2 means antiderivative of b minus antiderivative of a, we mean any antiderivative, not a specific antiderivative. Big F here is a specific antiderivative. It's the one that has -1 as the left endpoint. So what I should have done is use something else here to avoid that. Now maybe you didn't think of that, then it didn't confuse you, and that's not a problem. But I should have used something else, so I didn't get confused with that. So what's this mean? This means do the antiderivative. Now in this case, you actually could use t. Okay? So what's the antiderivative of that? We actually could do t squared minus 7t. But think about our right bracket. What would be on my right bracket? -1 to x, right? I mean, that's my integral, -1 to x, a to b, right? And so what do I do with that? I take x and I plug it in. Well, look what happens. See how t's not in there anymore? So I take x and I plug it in. I get x squared minus 7x. Okay, that's what I get if I plug x in. That's g of x. Minus, and now what do I get when I put -1 in? -1 squared is 1. 7 times -1. Look what you get. X squared minus 7x minus 8, which is the same exact thing we got before. It's kind of cool how that works. So now that we have learned fundamental theorem part 2 with this big F of b minus F of a, we actually can use it in problems like that with the right bracket. Okay? So, but I like both. I mean, I like knowing this way of doing it too. Do the antiderivative with a plus c. This is your initial condition. I think it's really good to understand both of them when you do it. All right. Well, that leads us into number 48 and 49, which are two others that I want to talk about today. And then if you have any others, that's about all I wanted to talk about. But if you have some other ones, we can do that. All right? Here's what 48 says. you're supposed to show that this derivative here is not equal to, I think, tell me if I write this wrong, I think I remember what it was. Right? You're supposed to show that the left side is not equal to the right side. Now what is that saying? What's the difference between those two sides? Okay, and you used the word integral and you used the word derivative. Well, you used that too. You said derivative of the integral. You said derivative, antiderivative. But isn't that the same thing, right? Zach was saying the derivative of the integral, but the integral makes us think antiderivative, right? So the left side is saying the derivative of the antiderivative, and the right side is saying antiderivative of the derivative, right? So if you put it in those terms, it kind of seems like they should be equal. I mean, really. Shouldn't you be able to do the derivative of the antiderivative? Shouldn't those cancel each other out and give you little f? And then here, if you do the antiderivative of the derivative, shouldn't that give you little f? Right? I mean, it seems like they should be equal. They're saying they're not equal. It's kind of like doing the square and the square root. The only difference is which one do you do first and which one do you do second, right? And does that make a difference? Well, actually, it turns out it does. Turns out it does make a difference. It actually makes a difference when you do square and square root also. Okay? This is the example I usually use. So let's look at that. So let's say you started with 9. That'd be like your little f. Okay? And we're going to do the square root of it. What do you get? Now, you don't get plus or minus 3, right? Let everybody be clear about that. When you solve this equation, you get plus or minus 3. Okay? Because that plus or minus 3 both work in that equation. When you do square root of 9, you get 3. If you want negative 3, you do the negative square root. Okay? So start with 9, do the square root, you get 3. Then square it, you get right back to where you started. Okay? So that order worked fine. Now, what if you do a negative 9? Well, you can't even do a negative 9, right? You can't do square root of negative 9, so that's not even an example. So anytime you start with a number that you can do the square root of, when you then square it, you'll get back to where you started. So that seems to work fine. But what if we go the other way? What if we start with 9 and square it first? 81. Let's square root of 81. That worked. What if we start with negative 9? Do the square root? No. You don't get back what you started with. If you start with a negative, the order matters, because here you can't start with a negative, so it doesn't hurt anything. Here you start with a negative, and you do the square, then you square root it, you don't get back what you started with. So there's a limit on when it will work. And that's really what this problem was saying. Did you notice it said, as long as f of a is not equal to 0, these are not equal? So that's kind of like putting a limit on when it will or won't work. So let's go through and talk about this. Let's use some notation first, and then I think it'll help you understand. What do you think of, what could we call this thing in here? Make it red. We call that antiderivative. What can we label it? Big F of x. Right? It's whatever that variable is right up there. It's big F of x, big G of x, whatever, but let's give it a name. Let's call it big F of x. Okay, now we're asked to do the derivative of that. Oh, wait, you know what I forgot there? Forgot plus c. Right? There's got to be a plus c on there. Right? Now you might have thought, well, that's just part of the big F, and that's true. But let's for emphasis, let's put the plus c there. So we do the antiderivative, you get a plus c. All right, now let's do the derivative of that. What do you get? Little f of x. What happens to the c? Goes away. All right, let's go to this side. Now, what would be a name we could give that? That'd be f prime. Of, well, careful. Would that actually be t? Because of this dt right here, right? It's just a derivative with respect to t of f of t. That's f prime of t. Now it's inside of this integral here. Right? See, that's still a t, so that would stay a t. Right? Now, what's this? This makes you think of the antiderivative of f prime which is f of x, and it's x because of this, plus some c. Now, here's where we'll call it the Sidney method. After Sidney. Here's where instead of putting a plus c, how about if we do fundamental theorem part 2 on this? Fundamental theorem part 2 says we do this antiderivative, which would be little f, and put in an x, minus little f, put in an a. Right? Isn't that the same thing? I mean, little f of a would be like our c. That's just a constant. A is just a number. Right? So these two say the same thing. See, like up here, I could have done that here. I could have done big F of x minus big F of a. Right? I could have written that there. Now when I do the derivative of big F, that's little f, the derivative of big F of a, since it's just a number, would just go away. All right? Well, look at this. Are they the same? No. Why not? Because when you do the antiderivative last, you get a plus c. When you do the antiderivative first, you get a plus c, but then when you do the derivative, the constant goes away. So it's just like that square root thing. When would they be equal? If f of a is 0. If little f of a was 0, then they would be the same. And that's what the problem said. It said as long as f of a is not 0, then these two are not the same. Okay? So what this just points out that the order you do the antiderivative would matter, because when you do an antiderivative, you tack on a plus c. All right? So, but a lot of that problem was about notation. If there was one like this on the quiz, yeah, it'd be a tough one, but not as tough now that we've kind of went through and talked about this notation stuff like that. Okay, let's look at 49. Now, 49 is one of those problems that shows up almost every time. In our packets, those 4 packets you did, I'll bet we can find one like this in at least 2 of those packets in the multiple choice section. Shows up on the AP test most of the time. But it's one of those that we see so seldom that you'll probably forget it. If you can happen to get it on the AP test, that's great. It's not hard, but it just never shows up very often, and we sometimes forget what to do when we see it. So here's what this problem said. What was it? Square root of, what was the problem? 1 plus t squared dt. They wanted you to find the derivative with respect to x, big F of x squared. Thank you. Cube root of 1 plus t squared. From 0 to x, so that's right, right? And, all right. Now, I actually love this problem in the book because I never understood, I learned, you'll see that the problems, the type of problems that are on the AP test are not written like this one. They're written a different way, which I'll show you when we're done. And I memorized how to do these problems, and I learned how to do them, but I never understood why until we started teaching out of this book, and I got to this problem, and I was like, oh, yeah, that's right. It's so cool that I'd never seen that before. These guys wrote it in a way that made it make sense. So hopefully you'll see that when we get done here. But this is big F, so we've seen things like that, not a problem. We can't do this antiderivative because of the 1 plus t squared in there. We could not do this antiderivative. You might say, we'll make it 1/3 power, raise it up. No, you can't do the power rule because it's got stuff on the inside. Now we did the chain rule with derivatives. We multiply by the derivative inside, but that doesn't work backwards. Actually, that's the thing we're going to learn at the end of the period today. We're going to talk about chain rule backwards. But you just can't do this antiderivative. Trust me. If you type it in your calculator, it won't be able to. Okay, it just won't be able to. Now, so what are we going to do with this? So we can't do that fundamental theorem part 2 kind of thing and try it. It's not going to work. So, all right. But here, now forget this up here. Okay, forget this part. Just look at what they're asking us to do right here. I think everybody in here should be able to do this. We've seen this before. Tell me what to write when it says derivative of this with respect to x. Tell me what to write. No. Forget that this means antiderivative, just a big F. Tell me what I do here. Big F prime, we do the derivative of the outside. We leave the inside alone. That's right. That's all I'm saying. It's just chain rule. It's just a basic chain rule. Okay? So we all ought to be able to look at this and say, oh, okay, derivative of that with respect to x is the derivative of the outside, leave the inside alone, tack on the derivative of the inside. Okay, now what we do from there, that's a little bit of another story. Well, one thing, what does big F prime typically mean? Little f. So let's write this as little f of x squared times 2x, right? Now, where in this problem is little f? It's the cube root thing. That's little f of t, right? The cube root of 1 plus t squared is little f of t. So if that's little f of t right there, then what's little f of x squared? That's putting an x squared in for t. So what would I have? Third root, right? Put an x squared in for t means you'd have x squared squared is x to the fourth times, and that's it. You're done. So when you think about that, that wasn't that big a deal. But now let me show you here in a second how this problem is normally given to you. And then you'll see why it's harder to remember. To me, the way they wrote this problem, it is not that hard of a problem. I mean, obviously, the first time you see it, you're not sure what to do. But now if you think about the steps we just did, that's not that hard. Do this. Well, that's just chain rule. Big F prime, leave the inside alone, tack on 2x. What's big F prime? Oh, that's little f. Where in this problem is little f? Oh, little f is always that thing in there. Little f of t. That's little f of t. Well, little f of x squared just means put an x squared where the t is. So we put an x squared right there. And then the 2x just comes down, comes along for the right. And you're done. But this is how this problem is usually given to you. And this is how I always saw it, and I memorized what to do, but I didn't, no one could ever give me a good explanation of why you did that. Here's how this problem is normally given to you. The integral from 0 to x squared. Now, we've never seen that, have we? We've never seen anything but an x up here, right? But on the AP test, they always throw one on the multiple choice, seems like. They have an x squared or an e to the x or a 2x or an x cubed or a sine x or whatever. They have something else besides a plain old x up there. Well, if you think about it, that's kind of what this was saying. What was it saying? It says this is big F of x, and they wanted to know something about big F of x squared. Well, that means put an x squared right there where the x is. So you can see why that's the same thing. Oh, wait, I forgot something. And then they always, and then this is on the outside, right? Do the derivative of that. So they always say do the derivative of, with respect to x of this. Okay? Well, let's think about what we did. Okay, it was easier when we saw it like this. What did we do? It was really two steps. It was this step, little f of x squared, which meant what? Just put an x squared in for t. So the first step was just take this x squared, put it in for t. So that's what we'll do on this one. Whatever's up here, we'll put it in for t. Because remember, derivative, antiderivative, they still canceling each other out, right? These two things are still canceling each other out. So our final answer still looked like the original, kind of, right? So they're still canceling each other out, but what we're doing is we're putting x squared in for t. And the second step is we're tacking on, now where'd that come from? It was the derivative of the x squared, so it'd be the derivative of this. All right? Now, let's talk about, and I'll come back to that. Here's the one I told you would be on the quiz. Now, I don't foresee 49 being on the quiz. But here's the one I told you would be on the quiz. Almost guaranteed. Okay? If I give you that problem right there, almost guaranteed this is going to be on the quiz because this is basically fundamental theorem part 1. What's the answer? E to the x to the fifth. That's the answer. It's derivative of the antiderivative. Derivative of the antiderivative. They cancel each other out. Especially when we do the derivative last, right? Because any plus c that's there is going to disappear. So there's no plus c because we did the derivative last. Derivative of the antiderivative is going to cancel out. So you're just going to get this, except not t, you'll have x. Well, think about the one we just did. It's the same thing. If you have an x squared or something else up here, it's the same thing. Derivative of the antiderivative, they cancel each other out. You're just going to get this, except with an x squared plugged in there. And you have to tack on the 2x, the derivative of that. Now that was the thing my professors always told me, in the old book that I used to teach out of, it just did it. You just had to memorize it. Like, why the 2x? And they would talk about chain rules, and I never understood it. But when you write it like this, it makes sense. That's why you tack on the derivative of 2x, because it's a derivative inside. So we take an x squared, put it in for t, and we tack on the 2x. Now in this problem, it's a lot simpler than that. We put an x in for the t, and we tack on the derivative of x. What's that? What's the derivative of x? 1. Yeah, so there's nothing to tack on. So, so it's really the same kind of thing. It's really the same kind of thing. Yes? Yes, because I know it must be important.
I don't have my backpack actually.
Oh, that is kind of important. All right, so this one, for sure, you're going to see something like that. That's just fundamental theorem part 1, right there. Okay? If so let's just, quick quiz. Notice I changed that from a 0 to a 2 to a 3. Does that matter? That changes the plus c, right? But when you do the derivative, what happens? That goes away. So that 3, whatever number's down here doesn't matter. Okay, so let's do square root of 1 plus x. Oops, that's bad. T dt. And not make that an x. Sorry. Make that a sine x. Quick, what's the answer?
Square root of 1 plus sine of x times cosine x.
Times on the outside of the square root cosine of x. That's it. Derivative of the antiderivative, they cancel each other out. You're just going to end up with what's in here, except with sine x plugged in for t, and tack on the derivative of the sine x, which is cosine x. Okay? These are some of the things that when I'm talking about notation and understanding the notation and being able to manipulate, work with it, kind of stuff. Okay? Now, so the rest of the quiz would be some of this chart stuff, which I thought most of you guys thought was pretty easy about increasing, decreasing. I got one on that word response packet that I want to talk about. That kind of is about that a little bit. Anybody else have another homework question? Any other homework questions I haven't answered? Yes, Joe. 58. Okay. All right. 58 says, is the average value of G prime from 0 to 3 greater than 1? Okay, good one. Because we just got to talk about average value. How do you write the average value of G prime? The integral of G prime from 0 to 3 over 3 minus 0. Now, you guys all have to look at your book on page 331, okay? The integral from 0 to 3, now that picture I think is G prime, I believe, isn't it? In 58, don't they give you the picture of G prime? Here's the problem. It says G of u equals the integral from 1 to u of little f of x dx. So I like how they did that. This time they put the x actually inside the integral and they made u be the variable, which is fine. Okay? All right, well, what's that mean? That means that g is the antiderivative, right? Little g is the antiderivative, which is fine. Lowercase can be an antiderivative, it doesn't matter. So little g is the antiderivative, so that means g prime is equal to little f, correct? So they give you the little f graph, so that means they also gave you the g prime graph. They're the same. Okay, so this is asking for the area under that graph from 0 to 3. Well, what is that area? What's the area from 0 to 2? How much? Pi halves? Negative pi halves? I would agree with that. It's a radius 1 circle, which would be 1 pi. It's half of that, so it's pi halves. And it's negative because it's below the x-axis. So that's the area from 0 to 2. Plus the area from 0 to 1. Now, from 2 to 3. What about the area from 2 to 3? Now there we just have to estimate. Just have to estimate. Count squares. What do you think? 1 1/4. Sounds good. Divided by 3, right? So what's that? Negative 1.57, isn't that pi halves? Plus 1.25 divided by 3. So this is roughly negative. Oh man, it's got to be. Well, it's got to be. Can't be greater than 1. No way, right? Because that's going to be negative quarter divided by 3. I mean, so that's, yeah, it's a negative. So there's no way it can be greater than 1. Okay? So that's a great example of an average value problem. I said an average value problem could be asked anytime you can do an area, anytime you can do a definite interval. Right there, we can do that. Now we have to estimate it a little bit. Okay? All right. Average value of g prime is the integral of g prime 0 to 3. Okay. Let's take a look at that 2011 packet. Because I think this is another problem. This is problem number 4. Maybe you tried it, maybe you didn't, that's fine. If you did not, all right. Now, the key parts of this are that they tell you this is little f right here, this graph, and they tell you what g is right here. So let me write that up here a little bit. So little g of x, and remember this is from 2 years ago, the AP test. So you can see how they use these area functions in these problems. Okay, so that's how they define little g of x. All right. So, and the reason I want to go over this is because this would be this could be on the quiz tomorrow. Some of this stuff could be in here. Now, some of it gets into some areas that's a little trickier, but that probably isn't going to be on here. But the basic concept of what's happening. So when I tell you that there are problems where you just got to kind of understand the notation, understand the concept of what's happening, you know, this practice on one like this is helpful for that. All right, so let's do this first one. It says find g of negative 3. Well, what's that mean? Put a negative 3 in here for x. So that would make this negative 6, and that would make this the integral from 0 to 3. Negative 3. Right? So what's the integral from 0 to negative 3? Well, here's, oh wait, that's going back this way. That'd be this area here. But it's backwards. So this is 9 pi divided by 4, because it's only a quarter of a circle, and it's negative. So this would be negative 6 minus 9 pi fourths. And this is a no calculator problem, just like our quiz tomorrow. Leave it like that. Don't try to multiply it out or estimate it or anything like that. Just leave it. Okay? That circle is negative because we're going backwards, 0 to negative 3. Okay? So, I want you to be able to do something like that. That's just understanding the notation. All right? Then they want g prime of x. Let's do that in red. Oh, well, that's just a derivative of g here, right? So that's just a derivative of this. So, you got two things added together, so you just do them each individually, right? So what's a derivative of 2x? 2 plus, what's a derivative of this? What is it? Richard, that's like 7 times you've done that. On the 8th one, you can get it? Come on. It's little f of x. right? It's the derivative of the antiderivative. It's what we were just talking about in 48, 49. Derivative of this is 2. Derivative of the antiderivative, cancel each other out. It's little f, but with an x plugged in for t. Little f of x, that's it. That's all you can do. You don't know what the equation of f of x is, so you're done. I mean, you could do it piecewise, but no, you don't. It didn't say to do it. All right. Now they want g prime of negative 3. Well, now that you have g prime of x, that's easy. G prime of negative 3 is simply put in a negative 3 in there for x. So this would be 2 plus f of negative 3, which would be 2 plus that point right there, which is 0. So it's simply 2. G of negative 3 is 2. All right, so that's just some stuff with notation. All right, now let's talk about B. B says determine the x-coordinate of the point where G has an absolute max on that interval. How do you find an absolute max? Several ways. Well, derivatives involved. How do you find absolute max or min? List of candidates where the derivative is 0, where the derivative is undefined, and the endpoints. So let's do the endpoints first. Now we're doing a max of G, so we're looking at G of negative 4, and we're looking at G of 3. Those would be my 2 endpoints. Where is the derivative 0? That's asking where is G prime 0? Well, what's G prime? G prime we just found up here in part A. It's 2 plus f of x. So where is 2 plus f of x equal to 0? When f of x is equal to negative 2. Now, I'll be honest, this problem caught a lot of people off guard 2 years ago. I hadn't done many like this. What's different about this function, first of all? Well, no, what's different about our original function we were given up here than any that we've done so far this year? It's got that 2x thrown in there. We haven't done any area function ones where we had an additional like 2x tacked onto it. And so our book doesn't have any of those. I hadn't done many of those, and then this came on the AP test 2 years ago, and it threw some people off. Okay, so now so they always try to come up with something that's a little different, kind of like I told you tomorrow's quiz might be something that hasn't been in the homework, but if you understand the concept, you still should be able to deal with it. Okay, so we want to know where G prime is 0. That's where f is negative 2. Well, where is f negative 2? Well, that'd be right down there. Well, where is that point? Now, be real careful. Yeah, can you estimate it? Remember the midterm where a bunch of you estimated what that point was and that wasn't good enough? We know this is a line. We can do the slope. This slope goes down 6 and over 3. What's this slope? Negative 2. So it's down 2 over 1, down 2 over 1. So how are we going to get to that point? Down 1 over a half. So what is this point right here? 2.5, negative 2 is that point right there. So the answer to this is when x is 2.5. So our list of candidates has to include G of 2.5. Now I'm going to do this the area way. I'm doing this as it's written up here. So G of negative 4, G of negative 4 would be a negative 4 plugged in right here. And right here. And right here. Correct? G of negative 4 would be negative 4 plugged in those spots. Well, what's that give me? That'd give me negative 8. What's the area from 0 to negative 4? Well, we already said this was negative, what, 9 pi fourths? And this would be what? 1 pi fourth? Positive 1 pi fourth? So negative 9 pi fourths plus 1 pi fourth? Negative 8 pi fourths? Negative 2 pi. So this would be negative 8 minus 2 pi. definitely a negative number, like negative 14 something. That, for comparison's sake, this is about negative 14. Remember, this is a no calculator problem, okay? Now let's do g of 3. Well, g of 3, that would be a 3 plugged in here, a 3 plugged in here, and a 3 plugged in here. So 2 times 3, that's 6. What's the area from 0 to 3? Well, that'd be a couple of triangles. What's this point right here, by the way? That's got to be 1.50, right? So from 0 to 3, I'm looking at this whole triangle here, and this whole triangle. Oh, aren't those going to cancel out? Those are going to cancel out. So it's 0. That's definitely bigger than this one. Okay? Well, okay, now 2.5. So now I need a 2.5 plugged in here. Oops. Oh. Yes, time out. Go. Oh, yes. Thank you. Thank you. Thank you. This is F. This is X. This is 2X. Yes, I'm sorry. So this was 6, and then this area was 0. So 6 plus 0 is, there you go. So that area is 6. Yes, I forgot about the 6. Okay, and now finally I'm going to do g of 2.5. So I put a 2.5 right there. So that's going to be 5. And then I need the area from 0 to 2.5. Well, that's going to be almost the same, except it's not going to cancel out, is it? So it's going to be this area and this area. Basically, it's going to cancel out. Let's just see it. This would be 1.5 times 3. That's 4.5. Divided by 2, that's what? 2.25? And then this one is going to go over 1 down 2. So that's 2 divided by 2 is 1. Yeah. So it's going to be 2.5 take away 1. So that's going to be 1.25. So it's going to be 5 plus 1.25. 6.25. There it is. There's my math. Now, the question said, what's the x-coordinate? So the answer would be at x equals 2.5. That would be your list of candidates area way of doing that problem. Now, I want to add one more possible way of doing that problem. Okay? That actually would be a little quicker than a list of candidates for this particular one. I'm not sure anybody would have thought of it. But right up here, I hate to lose all that, but right up here I said something kind of interesting. When we get g prime, what do we have for g prime? We had g prime of x was 2 plus f of x. You're to the point you're just guessing now, and you're like, okay, I got a 50-50 shot, right? Okay, 2 plus fx. This is little f, right? This is little f. Well, what's 2 plus f, little f? It's just shifted up 2. So this graph, so if I was going to graph the g prime graph, it would look something like this, wouldn't it? Something like that. This red one would be the g prime graph. And guess where it's 0? Didn't we solve that already? Remember, we found where it was 0 at 2.5, g prime, right? It was 0 at 2.5. Think of this as slopes. If they want the absolute max of g, right? And my red graph here is g prime. What's this tell you about what g's doing? Because this is positive all the time until 2.5. So the g graph is positive the whole time, increasing until 2.5, and then what? Decreases for just a tiny bit. Now, doesn't that fit with what we found? We found g of 2.5 was 6.25. We said that was the max, and we found g of 3 just after it was 6. Decreased just a little bit, didn't it? So it increased from like negative 14 something, boom, 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 all the way up to 6.25, and then decreased for just a little while. So your slope reasoning could be that, which would have been a lot less work, actually, if you would have just seen it. Sometimes the slope reasoning is harder. The area reasoning makes more sense, and sometimes the reverse. Okay? Either one of those rationales would have been okay on part B. Okay, stand up for 45 seconds. Stretch. Got to get our second win for this last little stretch run here.
Instead of oh. Yeah, I thought it was really awesome. Do you have any more of those packets we're just doing?
I do CDs for others.
All right, everybody sit down now. Everybody sit down.
The AP one. The
All right. Now, here, okay, write down this should probably go in your notes. This is not on the quiz tomorrow. All right? So you don't need to know. Not true. We have a small homework assignment based on this. This is the stuff that we're just going to get a running start here a little bit. And after the quiz, we'll be talking about this tomorrow. Now, so you write down this problem, and what's the first thing you notice about it? There isn't like an A and a B, right? The integral from something to something. We've never seen that before. Now, on your calculators, you might, if you got your calculators out, we're going to use them here in a second. But on your calculators, there are two different integral symbols you can use. One's got a box for the A and the B, and one doesn't. Now, you can use the one with the box for the A and the B and not even put anything in there. That's fine. Or you can just use the one that doesn't even have a box for it. But the question is, why aren't there boxes there? What's it mean if you have an integral and there aren't any places for the A and the B? Well, here's the answer. What's that? I think some of you guys had asked that, how do you get your calculator to do antiderivative? And the short answer for this is, that's exactly what it means. It just means do the antiderivative. But I want to, now that's the question. The C value, is there a C value, not a C value, what's going on? So you don't need to write this part now, what I'm going to write right now, okay? But I just want to talk about this for a second. So if I gave you this, what does that equal? What's that mean? I mean, who knows what equals, we don't know what F is, but what's that mean? What's the answer to that look like? No, come on. What does that number look like? It's a constant. It's a definitive number. It's a fixed piece of area. It's a constant. It's a number. A definite integral is just a number, right? -6 minus 9 pi fourths, like we just had a minute ago, or whatever that number. It's a number. It's a fixed piece of area. It's a constant. That's a definite integral when it's an A and a B. Then we went into problems like this. What's the answer to that? A function. Now, it's an antiderivative, right? So it'd be like, say, big F. But would you know the C?
Yes.
Because of the 2. So it'd be like big F of x minus big F of 2. It's a specific antiderivative where we know the C value. It's a specific antiderivative when we do an area function. And then the last one would be, what if we don't know A? Yeah, you could call that a non-specific antiderivative. How many are there? Infinite, because we don't know the C. So this is your big F plus C. Or you could say minus F of A, but since you don't know F of A, it's just some number, it's a constant plus C. It's a whole family of antiderivatives. Right? Because we don't know the A. But the bottom line is this. If you don't know what A is, if it's just a placeholder for some unknown left edge, and if you don't know X, in other words, X is this changing your input, is there any reason to even have them on there? You know what I mean? The A and the B mean something here. That's the integral from like 2 to 3 or 2 to 5. I mean, so they're important. The 2 here is important because it tells you what the C is. But this they're not really even important. So you called it a non-specific function or whatever. So that's what we do here. So when we do an integral where we don't have anything on there, that's like a to x. It's like saying, hey, this is the answer to this is the whole family of antiderivatives, so it will have the plus c on it. It will have a plus c, and we won't know. There's no condition that we know to put on it. Okay, so this is the symbolic notation we use to say find the antiderivative. This is like putting d over dx, which tells you to do the derivative. This is saying do the antiderivative of this. And since the fundamental theorem part 2 needs antiderivatives, and since our gateway test next week is all about finding antiderivatives, this is what we need to work on. Now, basic, simple antiderivatives we've talked about so far, the power rule, sine, cosine, just basic ones. This does not look like a basic one, right? This does not look like a basic one. So I'm going to go ahead and let you, as a matter of fact, it looks kind of messy because it's got a 2x. It almost looks like you need a product rule or something weird like that, right? The messier the functions got, the harder derivatives were to do, right? Isn't it true that your answers, when you did your gateway test, weren't your answers usually messier than the original problem when you do a derivative? But you know what? We're going backwards. So doesn't it make sense that if you're going backwards, that the messier problem you start with when you do the antiderivative might be less messy? Use your calculator. Use your calculator. Not always the case, but use your calculators and just type that in. Now remember, you got to put a time sign right there.
You always start with nice numbers.
Let's try it. It's in the little box, same place derivative is, same place the other integral symbol is. It's just the one without the boxes for the a and the b. So type in 2x cosine times, put a time sign in between the x and the cosine. That's important right there. What do you get? Sine of, it's not sine squared though, right? The x on the inside is squared. Now, here's what the calculator doesn't do for you. The calculator will not put the plus c. You have to do that. You need to write a plus c on your answer. Now look at that. That answer is neater, less messy than the original problem. That's not unusual. It won't happen every time. But it's not unusual that the problem looks worse than the answer ends up being. Now that you see that, doesn't it make sense that was the antiderivative? Because what are you going to do? Well, how do you check an antiderivative? Do the derivative. Derivative of the outside is cosine. Leave the x squared alone. Times the derivative of the inside. Just 2x. So that's where that 2x came from. Now the question's going to be, obviously we can't use our calculators on the gateway test, so how would we have known that? Now some of you might be looking at it and say, yeah, I see that. When you see something on the outside, when you see something sitting on the outside, check to see if that matches up with what's on the inside. Would it have kicked out? And you're just thinking in reverse. Now the problem is that doesn't always work very well. There are a lot of problems where you can't see that. Okay, so there is a technique that we can use, and it's called the U substitution, or just plain substitution method. The substitution method. Now on the quiz tomorrow, the antiderivatives are all going to be basic antiderivatives, simple power rule. We did some, might have some fractions in it, something like that. But where you do fundamental theorem part 2, you do them. Okay, all right. But going forward, we get to the gateway test. There's going to be some that do these kinds of things. So I just want you to work this with me. Let me show you how this is done and how we come up with this answer. So it's called U substitution. Here's how we start it. And if I were you, I'd write it very much the way I'm writing it right now. Okay? So off to the side, under it to the left a little bit maybe, we're going to let U equal x squared. Now, how did I know to let U equal x squared? Years of practice. Okay? You're going to have days of okay? And I will try to give you some hints along the way as to what to choose for you. Now, on your 4 or 5 problem short assignment today, it's going to be given to you. They're going to tell you what to pick for you, which is the whole point of the problem anyway. But there are some mechanics to go through, and so I want you to do that, where you don't have to worry about how do you know to let U equal x squared. Now, one of the most common things is the inside. If there's something on the inside, that's one of your best choices for what U to eat. Okay? Because basically substitution is the chain rule in reverse, which means it's going to involve an inside, something on the inside. All right, our next step is to do the derivative of that. So we'll write du over dx. Don't write u prime. You'll see in a second. We write du over dx, which is a derivative of u with respect to x, and what does that equal? 2x. Right? No x prime because we're doing it with respect to x. So it's just 2x. Okay? Now in the third step here, we're going to multiply. This is a kind of weird one here. We're going to multiply this dx over to the other side. So it looks like that. du equals 2x dx. Now, we are going to do that so often. I mean, every time, this is what we'll do. That we will start skipping this step right here. You'll just do, instead of du dx, do the derivative, then move the dx over. You'll just do du, and then do the derivative, and then tack on the dx. You'll just skip the middle step. Okay, because it's the same thing every time. We can bring the dx in. Okay? If you want to write all 3 steps every time, that's fine. But I think you'll get tired of doing it. All right. Now what? Now we do what the method says. It's called substitution. Now, I coach basketball, and I always use that analogy. We're going to take out the x's. Those are like the starters. And we're going to put in the subs. Kind of like you're in a drill team. Or do you have any subs?
Well, some days we
Some
have
nights, yes. Okay? So you're going to take out the starters, put in the subs. So the U's are like the subs. Okay? Now, remember, when you substitute on your basketball team, you got 5 out there. When you're done substituting, you got to have 5 out there. Unlike the girls' basketball team, the time we went to North Platte, we tried to put 6 out there and got technical 5. Okay, so no, we don't want any technicals here. Yeah, that was good. You got 2 math teachers on the bench as coaches, and we took out 5 and put in 6. But anyway, so here's how this is going to look. So the first substitution, I'm going to take out the x squared, and in its place, so we put in a new integral. And so in place of cosine x squared, I'm going to put, no, just this part. I'm just going to sub this part out first, like my point guard. Taking out my point guard, I'm going to put a new one in. Okay, I'm taking out cosine x squared. That's the same as cosine of u, right? Those. Okay, so what I did is I took x squared out and put u in its place. Okay, now what do I got left? I got 2x dx left. Oh. dx, 2x dx is the same as du. You don't want to mix x's and u's. So you want to end up with only u's in the problem, but you have to do it by substituting out the old problem. And you have to make sure you substitute out everything. Okay, so the 2x and the dx come out, and du goes in its place. Now, isn't this an easy integral to do? It's the antiderivative of cosine with respect to u. Well, that's what? Sine u. Don't forget the plus c. Now, some people, and some of you are thinking it, so I'll just go ahead and say it before you even say it. Somebody said it second one. People always, for some reason, they didn't worry about it when we did Fundamental Theorem Part 2, but they would worry about now what happened to the du. Right? People are thinking, what happened to du? Remember what the du is there for. It's just saying with respect to u. This integral symbol is saying do the antiderivative, and this is saying with respect to u. So the antiderivative of cosine u is sine u plus c. So the du is not there anymore. Okay? It's kind of like if I gave you this problem. If I said do the derivative with respect to x of x squared, what would you say? Now, did you ever wonder where the dx went? Did you ever where the d's went? No. They were just there to tell you to do the derivative with respect to x. You have 2x. So this integral symbol and this du are just there to say do the antiderivative with respect to u. So you've done it, so the integral symbols are gone. Because you've done what it said to do. Just like the d's and the dx's are gone now because you did what it said to do. All right, one last step. We're going to put the starters back in. All right, we're going to take the u out. We're going to put the x back in. So u was x squared, so we're going to put the x squared back in. And we get our answer. Okay? So, basically, here's what the u substitution technique does. It takes an integral that's hard to do, and one we can't just look at and see the antiderivative, and it turns it into a new integral that's easier. That's basically what it does. Okay? Matter of fact, that's most of the antiderivatives we do. Remember we had that whole big list of derivative rules to memorize? Product rules and quotient rules and everything? Turn to page 333. Turn to page 333. The good news here is there is not a whole nother big list of antiderivative formulas to memorize, like there was with derivatives. On page 333, that's it. If you memorize that, if you memorize those, basically, it might be missing one or something, but I don't think so. If you memorize those antiderivative rules, you'll be able to do it. Now, the problem is, so what's the difficulty in doing antiderivatives? The difficulty is what we're going to learn are methods that turn integrals into ones that are on page 333. So the difficulty will be learning the techniques and figuring out which technique will work in a certain problem. But what will always happen is we'll turn hard integrals into easier integrals that are like the ones on page 333, and then we'll be able to do it. Okay? So that's what it'll be like when we do it. So the next line on your assignment sheet says 5.4, page 340, 1 through 9 off. So those are 5 problems, just like the one we just did up here, where they tell you what to pick for u. They give you the integral, they tell you what to let u equal. Your job will be to do the du dx thing, and then your job will be to do the substitution and see if you can do that. They're pretty straightforward ones. So they're not easy. Now, 3 days from now, you'll look back at them and say, yeah, those were, yeah. Well, no, because you'll just practice them. You don't have so much practice at it. You'll be like, oh, yeah, that's how you do it. But until you kind of get the hang of it, it's okay? All right, so study for the quiz. All that stuff we talked about.